right? This phase over here, that I'm shading in red, okay? It is the phase where failure will occur. Okay? It is the phase where failure will occur. Okay? So we know that we are given a torque of 2,300 pound-feet. Okay? So we have to start writing this out. So we know that, so we draw our transformation first. Okay? So this is our Y. This is our X. Over here, this is our Z. Okay? Then from here, let's see what we have. We know that we have an axial load Px, and Px is driving at minus 2,500 negative pounds. Okay, and we know that it's always going to generate compression, always. Then we have a torque in the x direction is equal to 2,300 pound-feet. Okay. And then we have to convert this to 2,300 multiplied by 12. Okay, so 2,300, 2,760 pound inch. Okay. And then we have a moment in Z going at 1,500 pound-feet. So 1,500 multiplied by 12. 18,000 pound inch. Okay. So if we look at the question, we know that they highlight that this is a critical section. Right? That's where we shade the red, knowing that the failure will occur there. We know there's a torque of 2,300 pound-feet, we change to pound inch. A bending moment of 1,500 pound-feet, we convert to 18,000 pound inch, and an axial load of 2,000 feet. Okay. If the yield stress, so we know that the normal stress in yield is equal to positive 100 times 10 to the power 3 psi, right? And the shear in yield is equal to 50 times 10 to the power 3 psi. So we are required to determine the diameter, find diameter. Using maximum shear stress criteria, or theory, whatever you want to call it. Okay. So we know that the maximum shear stress is based on Tresca. Okay, let's start the problem first. Okay, so we know that it's from Tresca. So Tresca criteria assume, okay, Tresca criteria assume that tau max is equal to normal stress U divided by 2. Okay, he made that assumption. So why is this important? Okay, why is this important? So I'm going to, let's say we look at a material handbook. Let's say we look at the material handbook. Hold on. Okay, let's say we go and look at a material handbook. Where is my illegal textbook? Here it is. Okay. So you go to a page like this, near towards the end, right? I'll put this on. Okay, we take okay, we take this value. Oh, loud. Okay. Eugene. Sorry. My evil. Okay, my bad. This week is a really yeah, I have to forget this week. Okay, so you'll see a table like this. Okay, you will see a table like this. So now, for example, now if let's say you decide to use a material that is only given 75. Can you all see that? Right? You are only given 75, right? You are not given what? The shear. Okay. So if stress U is known and tau U or tau max is not given, okay, so like for this case, our AISI 302, and I think 302 is an austenitic stainless steel, and it is cold roll. Okay, cold, not good. Okay, so what you see, we are only given the stress U, right, is equal to what? 25, and not 25, 75 times 10 to the power 3. Yep, PSI. Right, the shear is not given, right? So from here, when you apply Tresca criteria, okay, when you apply Tresca criteria, you can calculate maximum stress is equal to 75 times 10 to the power 3 divided by 2. Okay. So this is equal to 37.5 times 10 to the power 3 PSI. Okay, you can calculate it. And not just that, you can also state that the stress U is equal to minus stress U. So i.e., the U strength in tension is the same as compression. Okay, the U strength in tension is the same as compression. In real life, okay, in most material, the stress U in compression is 1.33 times greater than stress U in tension, in tensile. Most material. Okay. If not given, make the assumption is the same. Are we clear? Okay. Don't come and I'm not given the value, I don't know. No. As engineers, we cannot say we don't know. The only thing that we don't know is is Putin going to lie again? Even that we know, right? Right? The only thing that we don't know is what is going to come out in the Lotto Max. The rest we can have an intelligent guess. So I want to draw your attention in the material down here. You can see that over here you have something that's 50, yes or no? Right? In compression is what? Whoa, 90. Another one over here, oh no, that's all we have, okay? So like I mentioned before, most of the tests on materials handbook are done in what? Tension. Easy to carry out, convenient, okay? That is the only reason. Right. So you can see some values are given in terms of tension and shear, right? If we were to use that criteria, let's say we don't know, it's 22 is tested, okay? So if we don't know, we can calculate that it's going to be what? So using Tresca, for this case, 38 divided by 2 is equal to what? 90, right? But when they actually did a test, they got the number what? 22. So it is what? Safe. What I'm trying to say is safe. It's conservative. So you'll be fine. Okay. So as you can see, if we go back to the textbook, okay, you can see, right? Come on, Eugene, seriously. You can see most of the time, I want you to focus on the tension and compression. These two down. Can you see? Right? Most of the time you have a lot of data in what? Compression, not a lot in what? Shear. Okay. You don't use the ultimate because ultimate are usually for what? Brittle material. Okay. When we design, we usually design with the yield because of ductile material. Are we clear? Okay. Right. So come back to here. Okay. So given now going back to our example, okay, going back to our problem, right? We are given that the stress yield, the normal stress in yield, and the shear stress, we are given the value. And this happened to be half. Right? You can see that this happened to be half, but there are magnitude that is given by the problem, okay, by the example. Okay. Okay, so we have a lot of things in mind. Okay, so what are the formulas that we are going to use now? Okay, what are the formulas? So the formulas that we are going to apply is we know that we have stress X, okay, and we have minus Px over A. Why I say minus? Because the load in the axial direction is in compression. Okay? So we know that where A is the cross sectional area. Okay, Px we know what is it. And then the next formula we're going to apply is stress X is equal to moment in Z, mz over Izz multiplied by Y. Okay, and Y over here is the radius of the shaft. And then one more in terms of we know there's a shear, and the shear is Tx over C divided by J. Okay, where C is also the radius of the shaft. So we have all this formula, okay, and then we have one more, okay, which we cannot use because we don't know the shear force value. In fact, if there is, we have to find the shear is equal to Vy over Izz Qz over T plus or minus Vz over Iyy Qy over T. Okay, but we were not given these values at all. Okay, we are not given what is our V at all. Okay, but anyway, I'm going to yeah, we don't know what they are at all. Okay, for this case, okay, we are not given. Okay, so the next thing we are going to do, we'll come back, we'll do failure analysis. okay, like what I've done on the shaft. Okay, I'll see you guys in an hour's time or less.